Alright, ladies and gentlemen, let's try now for a fourth time to see if we can finish this video. We had just determined at the end of the last video that the carrying capacity M for this wall loss situation was 100. That's the 100 right here, M minus P. Next question, what's the barrier population when the population is growing fastest, and what is that rate of change? I'm going to solve both of these together at the same time by sketching the graph. Now, I'm not actually going to do it here on the computer, but I would encourage you to take just a very brief moment and sketch the graph of this. Now, you may have to zoom out a little bit, but what you'll find is that it's a parabola. And if when you sketch that parabola, you'll notice that there is a maximum point right here. If you will take the time, use your calculator's capabilities to find that maximum. The two numbers that you get when you find that maximum are the two numbers we need for this answer. Now, the first number that you see there is a 50. When there are 50 bears halfway to the capacity, that is when the rate of change, dp/dt, that is when you see it tops off at a maximum. So the rate of growth is fastest when there are 50 bears. And then the y value that describes the rate of change when there are 50 bears, and that is, let me move the screen down a little bit, 20 bears per year. Alright, back up with the screen here. Back up a little bit. There we go. Alright, the next problem. This is going to be a massive problem. Take us about 4 slides, so if you don't have enough room there on your paper, you might want to grab some notebook paper. In 85 and 87, Michigan, the Department of Natural Resources airlifted 61 moose or mooses, or however you pronounce the word, from this park in Canada to another place in the Upper Peninsula of Michigan, blah, 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 blah. Basically, the moose population is increasing according to this equation here, and they want us to solve this differential equation. Now, I'm going to go ahead and tell you up front that while I'm about to do a very massive problem, and I would expect you to work it too, there's actually a shortcut for this in the end, and I'll show you that shortcut once we get there. But let's take this equation and let's solve it. Now, the first thing I'm going to do is I'm going to recognize this is a separable equation. I can move my dt over to this side, and I can move my p's over to this side. I can divide by p, and I can divide by 1000 minus p, and we have this right here. Now, ladies and gentlemen, again, I like to leave this number right here. This is a side with a simpler antiderivative or integral, if you will, and so I'll leave that number there. Now, if I look at this part right here, I'm going to take the integral, but before I can take the integral of this, I do need to separate it. This is a situation where we are going to want to use the partial fraction decomposition. So I know that this fraction here can be rewritten as something over p plus something over 1000 minus p. Select your p-values carefully. Obviously, I want a p-value of 1000 and a p-value of 0. Of course, before that, we do need to multiply by the least common denominator. When you do multiply by the LCD, we get this. Hopefully, you understand that, as we've done several of these already in this lesson. Now, if I plug in 0 for p, you get a 1000 right here times a is 1. Divide, a is 1/1000th, or 0.001. Plug in 1000 for the p value, that goes away. 1000b is 1, and again you see b is the same number, 0.001. Alright, continuing on, we'll take those numbers, we'll plug them in, and we are now ready to solve our integral. Now, before I actually do solve the integral, let's make life a little easier on ourselves. Those decimals and fractions are not good. Notice 0.001, 0.001, 0.0003. I could go ahead and multiply both sides by 1000. When you do, it makes, we backed up there. There we go. It makes that a 1, it makes that a 1, and it makes that a 0.3. Now, while that doesn't make the problem completely simple, it does, however, make it easier to deal with. Alright, now my integral laws, the integral of 1 over p will be natural log p. 1000 minus p, now on this one, ladies and gentlemen, I'll just do a little side note here. I would have to let u equal 1000 minus p right there, doing u substitution. du then would be negative dp. All that tells me is that I'm going to have to, when I do this integral, I'm going to have to multiply by a negative inside and a negative outside. And then it'll still be natural log, but that's where that negative comes from there, is because of that right there. Alright? And then the integral of 0.3 is just 0.3t plus c. Now the next step, again, is something that may or may not make sense to you. I multiply both sides by negative 1. Because I know where I'm going with this when I'm doing a logistic model, which is where we're heading. And I know that it would be better when I combine these logarithms together to have this one on top. So I multiply both sides by negative 1. Now, just as a side note, this negative c, you could have left it plus c. It does not matter, because negative or positive, it's still a constant. Now I can combine my logarithms. I'm subtracting, so I'll put this one on top over this one. Now, to get rid of the natural log, I'll take an e over to this side, and we have this right here. And now I'm going to move the screen down a little bit. There we go. The next thing I did, of course I accidentally skipped the next step there, but the next thing I did was I broke this up, and that's why I wanted the binomial on top. I did 1000 over p minus p over p, which is 1 right there. And then I move the 1 to the other side, and it gets us right here. Now we are getting very close to almost to the end of this problem. Getting pretty close. Alright, I do want a logistic looking formula, so I'm going to flip both sides. I'll flip the 1000 over p to make it p over 1000. And this is right now all over 1, so I can flip it and put 1 over all of that. Now let's take the 1000 to the other side. And now, ladies and gentlemen, I really have something that looks like a logistic equation right here, a logistic model. However, I do need to find this, whatever this e to the negative c thing is right here. Well, that's really not a problem, because it does tell me that at time 0, there were 61 moves. So now I can simplify this a little bit. Of course, that e to the 0 is 1. It does nothing. I can cross multiply 61 times that equals 1000 times 1. Divide both sides by 61, and we have this number. Subtract 1, and you see e to the negative c is this number. Well, what I'm going to do is I'm going to take that e to the negative c value right here, and I'm just going to plug it in right there. See, they're both e to the negative c. Alright, now we have this number, and this is our final logistic model, ladies and gentlemen. Now, in general, this is what a logistic model looks like. If we start out with the rate of growth in a logistic model, dp dt equals kp n minus p, which is what we've dealt with already, and we solve it, it gives us this form right here. Let me move the screen up a little bit. We might be cutting a little bit off at the top here. There we go. That's better. So in general, the P population formula is M, which you see we can get M from this equation right here. That just goes straight to the top. That's the carrying capacity. 1 plus A. A is going to be a constant of growth determined by an initial condition. E to the negative mk, T. Now T is going to stay T, but this E to the negative mk, that negative mk can be found by taking the m value here and the k value here and multiplying them together and then just putting a negative on it. Now, when you go through the homework, you'll notice that I've probably solved some of these the long way, but in some of them, I just use the shortcut. You are welcome to use the shortcut. Plug in m, take m and k, multiply them together, plug in there, and then you'll have an initial condition you can use to get A, and you don't have to go through all that work we just went through. And something is messing up, so I'm going to pause the video just a second and see if I can fix it. And I believe this looks a little better now. Ladies and gentlemen, we are now going to use our calculators. Now, I know you can't see all of the table at the bottom because the screen's cut off, but the data here shows a population of a place in Colorado from 1950 to 2003. And again, human population, animal population growth, these are best examples of logistic regression. We are going to use our calculators to come up with this formula. Now what I'm going to do is I'm going to move the screen down so you can see the whole table. Although we've cut off the title, hopefully everybody can now see the whole table. What I want you to do is I want you to pause the video. And when you pause the video, I want you to go to your calculator and I want you to plug in these values here for X, these values for Y. We've done this many times on our TI Inspires, or for that matter, TI-84s. And when you go to do analyze graph and you go to the regression line, pick logistic regression. Alright, so pause the video now and do that if you need to. Now, if you have done that already, hopefully your calculator gave you this or something real close to it. There might be a little decimal off or so, but that is the answer you should get. Now, based on this equation, what will the population approach in the long run? In other words, what is the carrying capacity? Well, we know that. That's this number up here. That's the M value. So around 316,000 people. Part C, based on the regression equation, when will the population first exceed 300,000 people? Well, now I'm going to take this P, and in its place I'm going to plug 300,000 right there, and then I'm going to solve. Now, this is a nasty thing to solve. The easiest thing to do would be to move this 300,000 to the right side so that I have a 0 here, then sketch the graph, and then use the 0 function on my calculator to find the value, and when you do, you get about 59. Now, T is 59. That's 59 years from the beginning, and 59 years from 1950 would be 2009. Then the last thing we want to do is, now that I've got this equation, I want to go backwards to this equation right here, this form with the differential. Now, I could try and take the derivative of this, or I could just get the K and the P values and plug them in. I'm sorry, M and K, not K and P, M and K. Well, first of all, I know that MK is this number right here, negative 0.1026. I also know that M is 316,440.7, which I will actually plug in right here in just a second. But now we can find K. So I'll take this number, I'll divide it by that one, and you get a scientific notation answer on your calculator. And there it is. So now I take that K value, I plug it in right here, I plug the M value that I already know in, and there is my answer. And there we go. Ladies and gentlemen, this homework will take you a little bit. It is not short, but it is very, very doable. So please take your time and come to class tomorrow. Ask me lots of questions.